Hi, welcome back to the science program. We asked the people of Maastricht which scientific question they would like answered. We got a question from the public asking how do subatomic particles know how to interact with each other? Therefore, this episode will be talking about particle physics. The world around us is made up of atoms, and atoms consist of a nucleus and electrons floating around the nucleus. The nucleus can again be divided into protons and neutrons, and those can be divided in what we call subatomic particles. In physics, one model is widely used, and this is called the Standard Model. The Standard Model was invented by physicists in the mid-60s and has been tested since. The Standard Model shows the different particles that make up all the matter in the universe and how these particles interact with each other by four fundamental forces. Particles that make up all the matter can be split into two types, quarks and leptons. Quarks can be divided into 6 particles, which are paired into generations. There are 3 generations. The first generation are the lightest and most stable quarks, and they make up all the stable matter in the universe. Then there's the second and third generation. These are heavier and unstable particles that will quickly decay into more stable ones. Furthermore, the quarks at the top row have a positive charge and the one at the bottom have a negative charge. The quarks in the first generation are the up quarks and the down quarks, and they are pictured in blue. Then we have the second generation with its charm and strange quarks, which are pictured in green. And in the third generation there's the top and bottom, or beauty quarks, that are pictured in red. Quarks only mix in ways to form a colorless object. To form a colorless object, usually 3 quarks are needed. These 3 combined will form an object with an electric charge of +1, 0 or -1. To visualize this, we brought along a model. For example, 3 quarks from each generation are present, and these 3 will form a colorless object. But also this is possible. These will also form a colorless object, as long as the electric charge is +1, 0 or -1. However, there's another possibility. Besides matter, there is also antimatter in the universe, and just like antimatter, there is also antiquarks. Antiquarks have the same mass, same mean lifetime, and the same spin as their respective quark, but their electric charge and other charges have the opposite sign. So, for example, this blue quark can also interact with its antiquark and form a colorless object. 2 quarks together are called meson. The second type of particles that make up matter are the leptons. Leptons can also be divided into 6 particles and are paired into generations as well. There are 3 generations of leptons, and just like the quarks generations, the same rules apply to these. Leptons in the first generation consist of the electron and the electron neutrino. Then the second generation is the muon and the muon neutrino, and the third generation has the tau and the tau neutrino. The top row here has an electric charge and a sizable mass. Then the bottom row are electrically neutral and have a small mass. Then there is the right side of the Standard Model that we haven't discussed yet, the fundamental forces. The 4 fundamental forces help us explain how the particles interact with each other. The 4 forces have a different strength and ranges. The strong force is the strongest, but it has a short range. Then there is the electromagnetic force, which is strong and it has an infinite range. The weak force is of course weaker than the forces mentioned before, and it has a short range. At last we have the gravitational force, which is the weakest of them all, but it has an infinite range. The forces are carried by particles called bosons. By exchanging bosons with each other, particles transfer discrete amounts of energy with each other. A simplified example can be seen in this model. Again, these represent the particles, and in between are bosons that carry a force. Only 3 of the 4 forces are proved to be carried by bosons. The strong force is carried by a gluon, the electromagnetic force by a photon, and the weak force is carried by a W and Z bosons. The gravitational force is predicted by the standard model to be carried by a graviton. However, this has not yet been proven. If you prove this, you most likely will win the Nobel Prize for Physics. Then there's only one thing left in the standard model that we haven't discussed yet: the Higgs boson. The Higgs boson gives mass to everything. The Higgs boson has only been proved since 2012 when a new particle was discovered. After that, physicists found out that this new particle is indeed the Higgs boson as predicted by the standard model. One of the places where particles are studied on a large scale is in CERN. And this brings us to another question that we received from the public.
I never got how the Large Hadron Collider functions, and I really would like to know that.
Based in Switzerland, CERN is the European Organization of Nuclear Research. The Large Hadron Collider is the world's largest particle accelerator. It is a 27-kilometer underground ring consisting of powerful magnets that must be kept at around minus 270 degrees Celsius. The particles are sent around in the ring in opposite directions and accelerated to near light speed. The magnets are used to control the path of the particles so that they eventually collide. The precision needed for collision is like firing 2 needles 10 kilometers apart and getting them to collide halfway. The energy from the collision is observed as small particles. Faster, higher energy collisions give larger particles, which are unstable and decay into smaller particles. Observation of formation and decay of the particles can help us to understand matter and the origins of the universe. The emitted particle's mass and other properties can be measured and compared with the particles that have been predicted by the standard model. It is through this careful comparison of observation and prediction that scientists at CERN hope to validate the standard model and announce the discovery of many particles now and in the future. At last, there is only one thing left to discuss. Particle physicists all have their favorite particle. Therefore, we went out and asked our own Maastricht University particle physicist, Jacco de Vries, what his favorite particle is.
Well, the right answer would be it's a piece of S meson, and that's because that's what a lot of my research is on about.
Let us know in the comments below which is your favorite particle. Don't forget to subscribe and smash the like button. For more information, click on this link to see the whole interview with Dr. Jacco de Vries.